Okay, so today we will discuss about Norton theorem. Norton theorem also like network reduction theorem. Using this also we only find out what is the current flowing through a particular resistance, and that is a load resistor. It is same like Thevenin's theorem, but here some step will be different from Thevenin's theorem. Like in Thevenin's theorem, what we will find like voltage across the two end, that is our Thevenin's voltage. But in Norton theorem, we will not do that. We will find out what is the current flowing in that load resistor. That will be our Norton current. And first we will find out that, again that we will find out what is the current flowing after the reduction of circuit. When we will make a simple circuit, that time we will find out IL, that is load current in that resistor. So if we will go for Norton theorem statement, the statement is telling, according to Norton theorem, in any linear bilateral network, irrespective of its complexities, can be reduced into a Norton equivalent circuit having a Norton short circuit current IN in parallel with Norton's equivalent resistance RN in parallel with load resistance RL. So if you go for Norton theorem, then we can easily understand that they are telling, like, this is your suppose this is your complex circuit, one complex circuit. If we apply Norton theorem in this circuit, then this circuit will look like this. This is our IN, that is Norton current. This is our RN, that is Norton equivalent resistance, and this is our RL. Okay, in simple Norton theorem, if we apply Norton theorem in any complex circuit, that circuit will be reduced to a simple circuit where one current source will be there, that is our IN. We call that Norton equivalent current. Then one resistance will be there like RN, that is equivalent Norton equivalent resistance. It's same like that is Thevenin's equivalent resistance. Then one RL will be there in parallel with these two, in where we will find out what is the current flowing in this resistor, that is our IL, means current through a load resistor. Okay, so if we go for Norton theorem, there are some steps like Thevenin's theorem to how to reduce a complex circuit to a simple circuit. So if we go for step, the step are telling, these are steps. They are telling, in first point they are telling, identify the load resistor, means they are telling in which resistor they are asking to find out the current flowing, that will be our load resistor. And second point they are telling, replace RL with a short circuit branch. The amount of current flowing through this short circuit branch will be Norton current, means they are telling after making short circuit up to that load resistor, we will find out what is the current flowing in that short circuit branch, and that will be our Norton current. Then third point they are telling, now remove the load resistor RL and replace all the active source by their internal resistance, like voltage source to short circuit and current source to open circuit. So this point is same as what we did in Thevenin's theorem. That's same. We'll make voltage source as short circuit and current source as open circuit, and we'll find out what is the total resistance in these two terminal, that opponent terminal. And 4 point is same, like we will find out what is the total equivalent resistance, that is our Norton equivalent resistance RN. Okay, so after that we make, like after finding out what is the Norton current, then what is the Norton equivalent resistance, after that we will make our simple circuit and try to find out what is the current flowing through the load resistor, and that will be our Norton, means that is our current flowing that load resistor. If we will go for draw the simple circuit, then suppose this is your complex circuit. If we will draw this circuit for Norton, then we will get our one Norton current, that is IN, and this current source connect to parallel with our Norton resistance, equivalent resistance, that is our RN, and one load resistor will connect. Load resistor will connect with parallel with these two, that will be our RL. in which branch we will find out what is the current flowing, that is IL. If we will go for Norton formula to find out what is the current, the simple formula we can write, that is IL is equal to IN multiplied by RN divided by RN plus RL. Okay, this is our Norton formula to find out what is the current flowing through this load resistor. Okay, so now this is the simplify of Norton theorem. Now if we will do a numerical, then it will be very clear to understand what is the concept behind Norton theorem. So go for numerical. So in this numerical, they are asking find a Norton theorem equivalent circuit for the network in shaded area of the network in given figure, then find the current through load resistor RL for value of 3 ohm. Means they are given a figure and asking to find out what is the current flowing through 3 ohm resistor. So this is our 3 ohm resistor. So they are asking to find out what is the IL value in this 3 ohm resistor. So we can simply tell that this 3 ohm is our load resistor. Okay, so if we will apply Norton theorem, means Norton theorem steps, what we will do first? First we will make this load resistor as short circuit branch, then find out what is the current in this short circuit branch, applying KVL or KCL. Okay, after that what we will do? First we are doing our first step. Okay, so this is our first step. First we will remove this load resistor and make it is a short circuit branch. So this is our one resistance. Then we will make this is our another resistance. Then last also 2 ohm resistance is present. This is our 2 ohm resistance. Then one battery source also present, that is 8 volt battery source. That will be 8 volt, and that is this side is negative and this is positive, negative, positive, and this is negative and this is positive, and it is 8 volt. And this resistance is telling that is 6 ohm resistance is here, and this resistance is 4 ohm, and this resistance is 2 ohm. Okay, and this is earthing. So then what we will know? We will make this load resistor as short circuit branch. So we can simply make it short circuit, and this is our A terminal and this are B terminal. Now we will find out what is the current flowing through this short circuit branch, and that current is our Norton current. So for that if we will see this circuit, what we are understanding? In this circuit 3 mesh is present. This is our first mesh, and this is our second mesh, and this is our third mesh. For KVL, applying KVL, if we will assign the current direction in same direction, like if you are taking in clockwise direction, then all the mesh current will be taken clockwise direction. If you are taking in anti-clockwise direction, then if you will take in all the current source in anti-clockwise direction, then it will be helpful to calculate the current value. So I am taking now in clockwise direction. So this is our I1, this is our I2, and this is our I3. So if we will now see this circuit, what we are understanding? Means in this short circuit branch only 2 current is flowing, 2 current source is flowing. Like that, if we will see I1 current, that I1 is flowing in downward, and this I2, if you will see that I2 is flowing upward. So there is in this branch I3 is not flowing. So if we will solve this mesh 1 and mesh 2 current value, then we can easily calculate what is the total current, and that current is IN, not Norton current. So there is no need to find out I3 value. So now we are going for calculating mesh 1 value, that is I1 value. So if you will apply our KVL like Kirchhoff's voltage law in mesh 1, that will be mesh 1 what? Here is 6 ohm volt, 6 ohm resistor, and current is flowing, so it will be drop the voltage. So you can easily write that minus 6 I1 equal to 0. So if you will see this, you can simply write our I1 value is 0 ampere. Okay, now go for mesh 2, that is our mesh 2. If we'll go for mesh 2, what we are seeing, that is I2 current is flowing, but this I2 is starting from this 8 volt from positive terminal. So we can simply write that is 8 volt, that plus 8 volt 8. Then if we will go for this 4 ohm resistance, what we are seeing, that this is I2 is flowing, so it will 4 ohm resistance will drop the voltage. So we can simply write minus 4 I2 is equal to 0. So if we will go for solving this, then minus 4 I2 equal to minus 8. So simply you can write I2 value is 2 ampere. Okay, now we got our I1 value and I2 value. Now if we means subtract these two value, then we will get our total Norton current, and that Norton current we can write like that. IN value equal to, that will be our I2 is bigger and I1 is 0, that's why we can write like I2 minus I1, that will be I2 2 ampere minus I1 value is 0, then it will be simply you can write that is 2 ampere, and that is our Norton current. So we can write here IN value is equal to 2 ampere. Okay, so now we go find out what is the total Norton current, that is 2 ampere. Now we are going for our draw second circuit, means second circuit. In second circuit, what we will do, we will remove our load resistor completely and make a two end like A and B end, and we will find out what is the total resistance across the two end. So now second circuit, this will be 6 ohm resistance. This is our A end and this is our B end, and we will make that battery source as short circuit branch. So it will be 4 ohm resistance is also here, that is 4 ohm, and we will make battery source as short circuit branch. So it will be look like this, and one resistance also present there. But what we will do, like this 2 ohm resistance is connected in short circuit branch. Okay, so it will, in this 2 ohm resistance no current will pass, all the current will pass with this short circuit branch, so it will not drop any voltage. So we can easily remove this 2 ohm resistance. There is no need to find out 2 ohm resistance in total. So if you will see this network, now 2 ohm with this 6 ohm resistance and this 4 ohm resistance are connected in parallel. So if we will apply parallel resistance, finding what is the total resistance for parallel, then we can simply write that is 6 ohm parallel with 4 ohm. That will be, I can write that is RN, that is means total Norton resistance, equivalent resistance, that will be, can write 6 multiplied by 4 divided by 6 plus 4. So it will become 24 divided by 10. So you can easily write that is 2.4 ampere. 2.4 ohm. So from this two circuit, we got our Norton current and we got our total Norton equivalent resistance, that is 2.4 ohm. Now we will draw our final circuit. In this final circuit, current source will be there. That Norton resistance will be parallel with that current source, and one load resistor will be parallel with that both two. Okay, so now we are drawing our final circuit. So we can write here like our RN value is 2.4 ohm. So now our total resistance means the final circuit is, it's look like this. One current source, that will be our IN, and that IN equal to 2 ampere, and one resistance that will be our RN, total equivalent Norton resistance, that is our 2.4 ohm, and one load resistor parallel with this, both with this two. Okay, so that will be our 3 ohm resistance. Okay. So now they are asking to find out what is the current flowing in this load resistor, that 3 ohm resistance. So that will be our IL. So now if we will apply here Norton theorem to find out what is the current. So if simply I can write that will be IL value equal to IN multiplied by RN divided by RN plus RL. So simply I can write that is IN value is 2 ampere. So 2 multiplied by RN value is 2.4 ohm. So 2.4 divided by this RN value is 2.4 and RL value is 3. So simply you can write this. So if we will solve this, then it will become like 4.8 divided by 3 plus 2.4, that will be 5.4. And if we will solve this, so it will come some ampere, and this is our IL. So simply we can do that. So this is the final answer. Okay, solve this and find out what is the answer. That is the final.